Hello everyone, joining the International Conference on Digital Technology on Driven Engineering 2025. This is Dr. Mohammed from Al Iraqi University. Today I'm pleased to present my work, a machine learning approach to binaural bits detection. Actually, this research introduced an innovative digital solution to a key challenge in neurotechnology by using AI to reliably identify these subtle brain modulating sound patterns. Let's begin. Before getting into the details of this paper, I would like to introduce the phenomena of the binaural beats, which is actually unusual auditory occur when the two slightly different frequencies are presented to each ear separately. As a result, for this difference of frequency, the listener perceives a third tone whose frequency matches the difference between the two original frequencies. Actually, these difference in frequency, what we call binaural beats, which could modulate a different brain state, including relaxation, attention, as well as sleep. That's why it become used as a kind of threat, what they call it as a digital drug. Actually, the frequency of range is in between zero point 0.5 and 30 hertz and covering a different band like delta, theta, alpha, beta, and gamma. So the aim of this project is to develop a smart system capable of automatically detecting for these binaural bits in a diverse range of real-world audio example. So the main objective is to combine number of machine learning technique and focusing on the characteristic of sound pattern known in a given piece of audio to address the fundamental shortcoming of binaural beats detection. The main challenges facing the exist methods like the Fourier transform and autocorrelation, it's that the difficulty when analyzing a real audio data, such as a high noise level, sound interface, or even the complex spectral component. These are the main challenges that face the traditional technique used by recent days. Our methodology it's proposed and involve a several sequential work units, divided the work into 5 units or 5 levels, starting by data acquisition unit, where we compiling an audio data set. Then the second unit, where the pre-processing data will be done and include the noise reduction, normalization, and segmentation. These are the 3 steps that we have done to pre-process the data before getting into extract the feature units. In feature extraction unit, we have focused on 3 sets of complementary audio features, represented by the first one, which is Mel frequency coefficient, spectral contrast, as well the zero crossing rate, along with their statistics. These 3 features are help highly to distinguish the binaural bits. And comparing to the previous study and the previous research, they were always using or depend one feature, so that's why the accuracy wasn't very high by detecting the binaural beats, while with using of these 3 features, it approved that help to high accuracy detecting for the binaural beats. In the fourth unit, where we're going to combine 3 types of machine learning, which represent by support vector machine and random forest, as well the convolutional neural network, as it's showing in the figure on slide in machine learning model. In the last level or unit, we are evaluation the 3 machine learning that we have applied by using the performance metrics and confusion metrics analysis to find out which one is the high accurate detected for the binaural beats. That was our methodology architecture, and I'm going to shift to the data set we have used to apply the paper. And our data set consists of 10,000 stereo audio samples generated under controlled environment condition and various binaural beats parameter. The positive sample of binaural beats, because definitely it will divide it into positive and negative, as well some of samples which include noise. So the positive sample generated from the linear sum of two pure tones. The beat frequency range between zero point 0.5 hertz and 30 hertz, and this is to cover the brainwave bands, and the carrier frequency range between 200 hertz and 2000 hertz, and this will be showing as a positive sample which include binaural beats, while the negative sample included pure tone, amplitude modulated tone, and ambient noise recording. This set for training we have divided into 70% for training and 15% for validation, as well 15% for test. Here are the three features that we're going to depend to extract the binaural beats. The first one is represented by, as I mentioned in previous figure, which is mellow frequency spectral coefficient, and here it's the compact representation of the spectral envelope, while the spectral contrast, which is represent the measured difference between the peak and dips. The last one is zero crossing rate, which is a quantified sign change in a signal. After pre-processing data, we have used these three models. And actually, in pre-processing data, we have used four steps. The first step is to convert to mono by convert all the stereo signal into mono using arbitrary vector averaging. Then we normalize these data by select to the unit variance. And the third step was the segmentation, where the signal was divided into 40 millisecond frame with 75 overlaps and Hamming window function with applied. After these three steps of pre-processing, we starting the feature extraction in order to start using the machine learning for training. The three machine learning module we have used, it's support vector machine, random forest, and convolutional neural network, as it's showing in the slide. The first one is support vector machine with radial basis function. Uh, this type of module have ability to learn a decision boundary in a high dimension feature space and generate a high quality decision boundary for audio classification. While random forest, which is considered the strongest against the overfitting and feature noise by aggregating prediction from the assemble of decision tree. The last one, which is convolutional neural network, the CNN algorithm, definitely it's capable to extract the hierarchical feature from any audio dataset and potentially compute the complex relationship between the carrier and the beta frequency. Of course, without explicit the feature engineering. The result on the test set showing a significant difference in detection performance, as it's showing in a table in this slide. Actually, there was three, as I mentioned, three algorithms. The first one was random forest algorithm, which is showing and achieved a perfect classification with accuracy. As you see, it's one, and the recall was also one. The F1 score was one. The confusion matrix was 100% positive and the negative as well. So it showed the perfect classification among the other module, while support vector machine showing also high accuracy, which is zero point 0.9, but it's accepted in a flow of incorrectly classification for one negative sample as a positive. And this is because of potential overfitting. While the convolutional neural network yielded zero result actually due to computational resources like insufficient training. It show like insufficient training. The most additional interesting result showing in this paper that the robustness against the noise, the performance of support vector machine and random forest classifier remain stable even when the signal to noise, which is SNR, what we call signal to noise ratio, dropped to zero with less than 0.5% degradation compared to the clean audio. While in most of previous study, when the SNR get dropped, it impact on the accuracy of the result of algorithms. The second interesting result is represented by computational efficiency. The random forest algorithm was the fastest in inference time. It's showing zero point 0.8 milliseconds per sample, making it computationally very efficient. This figure actually showing the accuracy vs the signal to noise ratio, and here it's showing the performance of the uh, random forest as well the support vector machine and how much it's accurate even with the dropping of noise. This figure also showing that the inference time per sample, and here it's showing the random forest achieve zero point 0.8 millisecond, while the support vector machine achieved 2.1 millisecond. And as we mentioned, that the CNN, the convolutional neural network, isn't achieved well in terms of time because insufficient training. So the main conclusion of this paper uh, that confirmed that the machine learning technique, particularly random forest classifier, have the potential to achieve near perfect accuracy level for the detection of binaural beats when trained on a well-designed set of audio features. Besides that, comparing to the previous study, that we found using of three features extracted could help by increase the accuracy of detecting of binaural beats, as well the addressing reality, which is provide a strong evidence for the ability of using the machine learning framework to address the pragmatic challenge of detection, as well accounting of real world variation like ambient noise, unlike uh, prior theoretical model. And definitely the machine learning approach successfully achieved uh, perfect detection for the binaural beats with help of using the random forest machine and support vector machine. Thanks a lot for your attention. Thanks a lot for your listening. And if there is any question or any query, I'm ready to answer that. Thank you so much and appreciate it.